Okay, so I'm going to draw the state transition diagram at the same time that we analyze this. So it's important that our output is a 1 when we're in state G. That is the state which we enter when our sequence is complete. But on our way there, we have to get the sequence which is requested. So A will advance to B on a 0 because that's the first digit. B will advance to C on a 1. C will advance to D on a 1. D to E on a 1. E to F requires a 0. And F to G requires another 0. So that's the sequence in order: 0, 1, 1, 1, 0, 0. And so often we want to start that way. But now I'm going to go through this and we're going to analyze this one state at a time to see what happens. So in state A, we have nothing useful, and so the possibilities are 0 and 1. Okay. On a 0, once we get a 0, the last digit is a 0, which is the criterion for being in state B, when the most recent input is a 0. Right? So on a 0, we meet the criterion for state B, we advance to B. Okay? And without any other digits, maybe we don't have the digits because we just started up, or we threw out a bunch of digits because there was no way for them to help us reach B, C, D, E, F, or G. So either way, we have nothing useful. If we get a 0 immediately at that point, our most recent digit is a 0 and we advance to B. If we get a 1, we can't match more than one digit because we only have one digit. And so we would fail to have the last input be 0. So all of these would fail and we would have to go back to A. So on a 1, A returns to itself because it fails all 6 ways that it could be at a higher state. So that's fine. Now in state B, in order to get to B, we have to have obtained a 0 recently. Most recently, we have to have gotten a 0. Okay. So you can see over here in this table, I forgot to point it out. So in state A, on a 0, the data becomes a 0, which meets B. And it would, on a 1, it becomes 1, which does not meet any state higher than A. In B, we have a 0 for sure, and our next result could be either a 0 or a 1. If it's a 0, our most recent 2 digits are 0, 0. And so on a 0, 0, 0 does not match 0, 1. So we fail option 2 here. But we do pass the 1 option. If our last 2 digits are 0, 0, our last input is at least a 0. So we meet the criterion to be in state B. So on a 0, B would return to itself, because that 0 then forms having a 0 available to initialize the 6-bit sequence. We'd be 5 digits away. On a 1, our most recent 2 digits would be 0, 1, and there is a check for that. If the last 2 digits are 0, 1, which is the longest we could possibly match, so these 4 are no by default, but the last 2 digits, if we're in B and get a 1, we would pass this check, and thus we qualify to go to state C on a 1, which is what we drew here. And so that would correspond to, after a new 1 following state B, 0, 1 does match its last 2 digits, match the criterion for C, so we go to C as we've drawn here. So we're done with that. Now we can start in C. To be in C, the only way we're allowed to be in C is if we have had a 0, 1 most recently. Our options at that point, we could get a 0 or we could get a 1. If we get a 0, the longest we could match is 3 digits, but 0, 1, 0 does not match those 3 digits. The last 2 would be 1, 0, but 1, 0 is not 0, 1, so we fail that check as well. But our final digit would then be a 0, and so we do pass the check to be in B, which is what I've written right here, 0, 1, 0. You check that against 3, it fails. Check the 1, 0 against the 0, 1, it fails. But you check the 0 against the 0, it passes. So we would go to B in that situation. So C returns to B on a 0. There you go. On a 1, the 0, 1 would be followed by a 1. It could pass up to a 3-digit check, and it does. 0, 1, 1. 0, 1, 1 is what we got if we get a 1 while in C, and that will take us to state D in 0, 1, 1. So a 1 advances us to D. And so hopefully this sort of shows what we're about to do. So as we go, we just continue. We've figured out 0 in C, a 1 in D. And so we just keep following this table. To be in D, the only way we're allowed to be in D is if we've got a 0, 1, 1. At that point, we can get a 0 or a 1. If we get a 0, 0, 1, 1, 1 is not 0, 1, 1, 0. 1, 1, 0 does not match 0, 1, 1, so we fail that check. 1, 0 is not 0, 1, so we fail this check. But the last digit would be 0, which passes this check, and therefore we would meet the criterion to be in state B on a 0. So D sneaks in there on a 0. Right? So state D, get an additional 0, it would be 0, 1, 1 followed by the 0. That takes us to B. On a 1, 0, 1, 1, 1 is the 4 match. That's the longest match that's possible. And so we would meet the 4 match, the criterion to be in state E, which is why a 1 in D takes us to E. So the process continues. I need the video to stay fairly short. So in E, a 0 takes us further, because that would give us the 0, 1, 1, 1, 0 at that point if we got a 0 after the 0, 1, 1, 1. So we would advance to F. In E, on a 1, so here's E, row 9, swing across. E on a 1, E begins 0, 1, 1, 1. The additional 1 would give us another 1, and it's not the 5-digit sequence. Since the last 4 are 1s, all the rest of these checks have a 0 in them, so they can't pass any of these. None of these checks are passed once our last 5 are 0, 1, 1, 1, 1. We fail all 6 and therefore return all the way back to A if E obtains a 1. If we get to F, we can only do so if the last 5 digits are 0, 1, 1, 1, 0. On a 0, that would complete the sequence, take us to pass all 6, send us to G. The other option, we could get a 1, so row F here runs all the way over here. On a 1, we don't match the 6. The last 5 do not match that last 5. The last 4, there's a 0 there, there's a 1 there, so it doesn't match. There's a couple of mismatches there. 1, 0, 1 does not meet this, but there is a 0, 1. And so as we do pass this check, when we pass this check, we run it all the way back, that's C. So we get to C by getting a 0, then a 1, which in that situation where we're in F and get a 1, The 0 got us into F, and the 1 would take us back around to C. Because we would have had the 0, 1 that takes us to C, which makes some sense. And then from G, we get to G by having 0, 1, 1, 1, 0, 0. So there are two choices. We could follow that sequence up with a 0, in which case you can check the 6, the 5, the 4, the 3, the 2, and the 1. The only check that we pass is the last input would be 0 at that point. So G goes to B on a 0, and on a 1, we would terminate the 6 digits with a 1, and you can check the 6, 5, 4, and 3, and we'll fail them all, but we do pass the check to be in state C here, the 0, 1 ending. So G would return to C on a 1. So this is kind of a really complicated diagram. You can derive the rest from the diagram, but I am going to use this table now just because it's a little bit easier to keep track of. So I carefully described in any given state A through G, what is the output while we sit in it, and if we get a 0, where do we go? If we get a 1, where do we go? So you can follow the arrows. So our next chunk of our table is going to say, in state A, if you get a 0, where do you go? We would go to B by following the arrows. There's just a lot of arrows, so I'm going to use this tabular version to construct. So in the interest of time, I'm not going to run this all the way out to the end where we implement this using JK or D flip-flops, since I did cover it in the counter video. But I wanted to post a little bit of help with the design process here. And so we have our raw input here, and one little trick that you can use when you're drawing this table that can help is to label the state letters off to the side here. So what I've done is I've made it so that the letters go A through G, and so these are the codes in order. So 0 is A, 1, 0 is A, 1 is B, 2 is C, then you have D, E, etc. We go up to G. The code 111 is not in this list. It's not used. So I marked it as does not exist. And because of this table that's over here, and you can just barely see this, but this is get 0 as an input, this is get 1 as an input. And constructing it in a tabular format like this, you can do it from the state diagram, but once I've written it this way, now it's just a matter of saying in A, on a 0, new state is B. Then, so these are all the 0 destinations in order, which is nice, because then A, B, C, D, E, F, G on a 0 is what we're talking about here. So in order, it's these. So I can just get away with, and I'll need to do a paste special, but values. And so then in the state which doesn't exist, the destination doesn't exist either, which is fine. And then over here we have the 1s on a 1 in A, B, C, D, E, F, or G. So we'll copy those, go here, we'll do another paste values. And again, this one does not exist. And if you write it in terms of letters, now it's super easy. So all we have to do is go, okay, this is B. Well, I'm just going to pick up the code for B, and everywhere which our destination is B, I'll just drop it right in there. Okay, which is all of those. There are a couple C's running around here, so let's grab C. So our destination is supposed to be C, here, here, and here. That does not exist. We get to put don't cares. Because we don't care where it's going, since the state is not used. So there's the C's. Now we should have a few A's. So let's grab them. So A is here, here. Yeah, the rest of these I'll have to shift over. So there should, all of these are destinations at some point. So there's got to be a D in here somewhere. There it is. There's going to be at least one E. E is located here. There's at least one F. F is the destination here. And then G is going to be the destination once as well. Okay, so these I'll center again. Oop. And then the output has nothing to do with where we're going. In the Moore machine, the output is a function only of the present state. And so we can actually just take these outputs. These are the correct outputs in order. So the output, while we're in state A, B, C, D, E, F, G, are these, which is a nice thing about the Moore machine. So I'll paste the values there and the values there, which are the correct locations. For the state which does not exist, we get to put X's in there. We'll center that again. So from here, you have to take the Q's and the Q pluses to determine the J's and K's, etc. So I won't go over that in detail, but I will fill them in real quick. Or no, but you can follow it. It's just a matter of applying that the excitation table from here. And then your K-maps will be in terms of the input as well as the state variables. So this would be a 4-variable K-map. The inputs will be the raw input X and the present states Q2, Q1, and Q0. And then you'll need, depending on what we're doing, let's say it was D2, D1, and D0, then it would actually be pretty easy. With D flip-flops, it would just be the Q pluses, just like before. And so this isn't too bad at all. So this one's easy to copy and paste. And so now I can set this up in Logisim and construct it. And so on a test, you wouldn't be able to do this, but on a test, it would be a smaller machine. But if you're still working on the Moore Mealy project, this is the idea, and then we would just paste this information in. So I'm going to pause for a second while I line that up. Okay, so I'm going to open up the combinational analysis. You can press Analyze Circuit if you want to analyze what's on the board, or if the board is empty, it will become the same as combinational analysis. But if you don't want to rewrite the contents of combinational analysis, you should pull it from the window option. So I'll do that real quick. And so in this table, the inputs are to the combinational logic portion are in order X, Q2, Q1, and Q0. The outputs are on this side and are the raw output Z, the D2, the D1, and the D0. So now this is just a matter of asking the combinational logic to help us, the combinational analysis. So I'm going to copy the Z, D2, D1, D0 in order. So you got to make sure these are in the right order, or you manipulate them over here until they're in the correct order. Put this in, build it, And so then this is the more 011100, which is the name I already gave it. So it constructs this for us, makes it super easy. So you won't be able to do this on the test, but on the design project, you're good. So then now it's just a matter of sending this information around. So we throw in the memory portion that our original diagram said we need. And so D just sits here, this D sits here, this D sits here. And we just run D0 in here and Q0 around. We swing Q1 around and then drop D1 into place. We drop D2 into place, sweep Q2 around. Okay, I held on to those just long enough to know where to put them. And I just need a clock, and it should begin to operate right away. So clock. And so if I hand it the code it's interested in, which was 0, 1, 1, 1, 0, 0, it outputs a 1. If you input anything else in order, it will not go to 1, and it should be keeping track. So that's the Moore machine. You would do Carnot maps for this in general, but we let Logism do it for us. And now I'm going to cut this video here, and we'll switch to the Mealy machine. There's going to be only a couple differences, but I will cut to that right now.